Hello and welcome to How Space Elevators Work, Physics Concepts, presented by the International Space Elevator Consortium. Our speaker today is Dr. Dennis Wright. He is the ISEC Vice President and Nuclear and High Energy Physicist, formerly with the Stanford Linear Accelerator. He received a BS in physics from Case Western Reserve University and his PhD in nuclear physics from the University of Illinois at Urbana-Champaign. Dr. Wright has performed experiments in nuclear and high-energy physics at Los Alamos, Triumph, Stanford Linear Accelerator, and at the Large Hadron Collider. He joined ISEC in 2013, and his foci is in dynamics, electrodynamics, and simulation. Dr. Wright and his wife live in Santa Fe, New Mexico. And with that, I'm going to turn things over to Dr. Wright.
Thanks very much, Karen. As you can tell by the bio that Karen gave you, I have gone through something of a 90-degree course correction. Space elevators probably in some ways couldn't be more different than high-energy physics, but I find them both fascinating, and so I'm really happy to be working on space elevators. So today I'm going to speak about some physics concepts of space elevators. It's going to be a general level talk, but I would like to first gauge the audience and see where everybody is at and what your backgrounds are. So Karen has a poll, which is coming up now. And you can check which of these categories applies to you.
And it sure looks like everyone is done voting. I'm going to give you a couple seconds more. All right, and as you can see, we have space elevator, space enthusiast is 50%, engineer scientist 41%, and we have a couple students with.
Okay, great. And so let's, with that, proceed. And let's first start about where we are today with space elevators. So I'm sure most of you have heard a little bit about them in one way or another, but let me give you a little bit of background. The concepts, the first scientific concepts for space elevators have been around for quite a while, since the 1890s. So the guy you see in the center there is Konstantin Tsiolkovsky, and you may know him for his invention of the rocket equation. So he put forth the equation that said, given the amount of mass of a rocket on the pad, what percentage of that mass is going to make it into orbit or wherever you want to send it. And it's a very strict and difficult equation in terms of what it means for engineering, because you can expect on the order of only 1% of the total rocket mass to get where you want it to go in the solar system. Could be a little bit more, could be less, depending on where you want to send it. So the rocket equation is a hard master, and it causes a lot of the expense of what we're dealing with today. And even with reusable rockets, it's still going to be very, very difficult. And so it is somewhat fitting that the same person also conceived of space elevators in a scientific sense. There have been fables and stories about space elevators by other names, but he was the first one to actually give some scientific thought to it. And he considered it as a tower, so a compressive structure, and recognized that if you built one tall enough, that you could use the Earth's rotational energy to launch something. He also obviously quickly realized that such a structure would be prohibitively massive, but the idea was put out there. And so that was more or less the beginning. And since then, there have been some serious concepts starting in the 60s. And perhaps culminating in 1999, there was a NASA Advanced Concepts Study by Brad Edwards. And he put forth the idea that a space elevator could actually be built if you used a cable. So no longer a compressive structure like a tower, but something which is suspended. And so he did that study and published it. He did a rather nice book on the results. And one of the pictures from that book is on the right-hand side. And that's one of his renderings of how a space elevator might look. And so it is going to be a cable suspended. He also concluded that in order to do this, we're going to need a very strong material. And strong materials do, in fact, look to be on their way. So I'll say a little bit about that later, but the picture at the bottom center is an electron microscope picture of graphene. And so you can see the arrangement of the carbon atoms in a hexagonal pattern. And so that's one of the materials that we're going to look at. And so with materials on their way and the physics more or less understood about how to build a space elevator, it's really time to start thinking about building one of these things. And this webinar today is the third webinar in our series. The first one was Pete Swan. He's our president, and he talked about space elevators today and what they can be used for. And if you want to see that, that's at the ISEC website under our recorded webinar. So just go there and click on that, and you can see that for. So let's now start with the physics. And I'm going to talk about how to build a space elevator from a physicist point of view. So let's, we always like to start with simple things. We'll start with a static space elevator. So what holds it up? And then we'll add some dynamics. So this thing is going to be moving in several different modes. We wanted to consider that and what it takes to keep it up. And we're talking about elevators, and an elevator isn't much good if you don't have elevator cars. And so we have to add climbers, and they introduce additional complications which we have to take into account. Once these are all added, then we have to consider that this space elevator is going to be in a rather complex environment. So we have to put it in an environment, and I'll talk about that a bit. And finally, with my tongue firmly in my cheek, I will say that all the rest is details, so I won't go into that. Now, let's go back to Physics 101. I know we all love that course. And the thing we want to talk about right now when we're talking about statics is the balance of forces. So let's look at the right-hand side. We're going to try to suspend a brick. So I have a red block there and a wire supporting it. And so how did we do this problem? We needed to somehow balance the force of gravity with a wire pulling up so that the brick stays in place. And in Physics 101, they always cheat because they always say use a massless wire. Well, okay, now we have to be realistic, though, if we're going to build a space elevator. And we have to take the mass of the wire into account. And so if we look at the brick, you see I drew a green box around it. So not only do we have to take into account the brick, we have to take into account whatever is inside the green box. And so I have extended it to include a little bit of the wire, which has some mass. So that means that the force outside of the box, outside of the green box, has to support the brick and a little bit of the wire. And now as we increase the box, we have more and more wire to be added. So the wire not only has to support the brick, but its own weight. And as you go up and include more and more wire, you include more and more mass, and you find that you have essentially an exponential increase. And this is what Tsiolkovsky ran into when he was thinking about building a tower into space. So it's just a prohibitive amount of mass, and so we're really sunk. And of course, the Physics 101 problem usually says that gravity is a constant because we're operating at the surface of the Earth. But since we're really building something out there, we can take advantage of the inverse square law of gravity. So that helps a lot, but it's still not enough to overcome that exponential. So we're still in trouble. So what do we do? Well, we have centrifugal force. So this is going to help. This comes back to the old example of taking a bucket of water on a string and rotating it around. As you face the bucket of water, you can see the surface of the water is perpendicular to the ground as you rotate fast enough. So centrifugal force is helping you there. Now, whenever I talk about this, I can't help but show my favorite XKCD cartoon. So I'll give you a few seconds to read that. And I don't know about you, but I personally am disappointed that James Bond cannot do coordinate substitutions in his head. So we'll go on from there. So we are doing this problem in a rotating reference frame. So the Earth is rotating. There will be an outward force, which will eventually compensate gravity. At the surface of the Earth, there's still a little bit of this force, but it's very small. And we have to go out quite a ways before it becomes appreciable. And just to clarify, I know most of the people in this audience, being engineers and scientists, know this, but just to set it straight, we are talking about centrifugal and not centripetal force here. If we do this in an inertial frame, that is a non-rotating frame, then yes, we would use centripetal force, but it gets a little complicated in a rotating frame. And so centrifugal force simplifies the equations a lot, and that's why we like to use it, and we call it by that name. Here's a diagram of what we can expect the sum of the forces to be. So we are going to now look at the acceleration of an object which is above a fixed point on the Earth. And down below you see the x-axis, the radius in thousands of kilometers. And on the y-axis, we see the acceleration that is felt by some object at that fixed point. So our cable is going to extend from the surface of the Earth out to 100,000 kilometers in altitude. And we can just look at the curve. And near the Earth, you can see that it is about 9.8 meters per second squared, as expected, and that it falls rather dramatically. So this is the inverse square law coming in. And at around 2 Earth radii, the centrifugal force starts to become noticeable. It's about 2% or so at that radius, but it really picks up steam. And by the time we get to this dotted line, that is geosynchronous altitude, or the altitude of geosynchronous orbit. And that is where the gravitational force is balanced by the centrifugal force. And that's why we have lots of communication satellites up there, because they maintain the same position as the Earth rotates. But we keep going out further, and we see that now centrifugal force is taking over, and in fact is providing more outward force. And this ultimately is the force that we need to overcome both the mass of the cable and the gravity. So given these forces, what would the tether be like? We could make a simple, long, rectangular ribbon, which is the same width at any distance. But this is not the most efficient use of the tensile strength that we would have of whatever material we wanted to use. And so we can be better about this by putting more mass where the stress is the greatest. Now, this leads to kind of a tapered shape. So the cross-section, if you will, of the tether varies as a function of altitude. And it increases and increases until you get to geosynchronous orbit, and then it decreases. So this particular shape that I'm going to talk about is of great advantage because it has constant stress all along the tether. So if you're an engineer, you know that that's a very good thing. And this constant stress taper was invented by Jerome Pearson, who is one of our members. And here's what it would look like. I've made a plot of constant stress tether shape. And so if you were to make a flat tether, as we envision making, then it would be very, very thin, and it would have this cross-sectional shape. And so at the Earth's surface, it would have an area of probably a few square millimeters, depending on what our load would be. And you can see that the width increases very, very rapidly. This is mostly taking care of the inverse square law of gravity until you get to geo, which you reach your maximum stress and therefore your maximum area. And then it slowly decreases as you go further and further out. We get to the point where we call this the apex anchor. This is where we would put a counterweight. We could continue this ribbon out for a long way and use just the mass of the ribbon to counteract the gravitational force. But we can also attenuate it and put a large mass there at the apex anchor. And that does the same thing for balancing the forces. So all of this implies that we need something very strong still. And it looks like a tensile strength of 49 gigapascals would do the trick. So just to put that in familiar terms, that is about 200 times the strength, the tensile strength of steel. And that sounds like a lot, but it looks like we have materials that are going to do that. There's another consideration, and that is we want a strong material, but we also want a light one. And so here I am assuming that we're going to make it out of carbon nanotubes or single crystal graphene or something like that. And the density of those things is around 1,300 kilograms per cubic meter. If we were to use steel, then it would be roughly 3 to 4 times that. And we would not have as efficient a system. And so what we like to do is talk in terms of specific strength. That is the tensile strength divided by the density. And so if we take these two numbers, 49 gigapascals and 1,300 kilograms per meters cubed, we get 38 megayuries. And that's a megayuri is a special unit that we use to denote specific strength. So with that in mind, let's go to the next page. And this tells us a little bit about the materials that we are interested in. So definitely, if we don't have the strong material, we don't have a space elevator. And as we saw in the previous slide, we need a specific strength of 38 megayuries. It's a little bit more than we need because we allow for a safety factor. But what in the world is this strong? Carbon nanotubes look like they will be. The leading candidate right now is single crystal graphene. So this is an amazing material, and that is shown in the upper right. It's a picture which could represent either single crystal graphene or boron nitride, essentially 2D materials. This is a single crystal, and very, very thin because we're talking about an atomic thickness. The alternative is the carbon nanotube, which is a 1D material. It's a tube, but it's small enough that you can think of it as just a line. Also strong and made of carbon. Now, the second webinar in our series was given by Adrian Nixon, who is now developing the means by which to mass produce single crystal graphene. So in the laboratory, we have already samples which are half a meter long, and Adrian's group will work to make them much longer, and that is the key. Once that is there, we can start building. So I encourage you to see his webinar, also at the ISEC website. Now, I think we have a pause for some Q&A.
Yeah, we have one question from Justin. He says, am I understanding correctly that at its widest the tether would only be 33 millimeters, or was that slide not to scale?
The thickness there, what I didn't show on that slide was the thickness. I made it rather thick. In fact, it would be very, very thin, and we expect that at the widest part, it would probably be on the order of a meter or two, maybe bigger.
Another question came in. Can any of these materials be continuously printed?
That is the question of the day. And so Adrian is online. He is working on a process to do just that.
Okay, I do see a few other people are typing. What is the advantages of using the unit of Muries?
Megayuries? Yes. Really convenience if you do the equations for the statics and the dynamics of a space elevator. You always see this ratio come in. So it's the tensile strength divided by the density. And rather than keep writing those two things down all the time, we just make that ratio. and it turns out that the numbers come out conveniently. So it really is an issue of convenience. Also, it was made, the name was made to dedicate Yuri Artsutanov, who was one of the co-inventors of the modern space elevator.
How can repairs be conducted on such materials should that be needed?
Another very good question. Depending on the material, it would probably be something like having carbon in its gaseous form allowed to come in contact with the fault in the tether, and then it would bond into the matrix of the material. And the details of that are something that I think have yet to be worked out. But once again, that's a question that perhaps Adrian would know more about than I do.
All right, and of course Adrian did chime in, and he did mention that there is a process in Korea to print graphene continuously. But another question, what is the minimal practical width for the climber to hold on to?
Could you repeat that again?
Sure, what is the
the minimal practical width?
Practical width,
yes. I see. Actually, I don't think it's the width so much as the thickness. So what we have to worry about with a climber, and I'll get to the climber in a little bit, is what is friction going to do, and how much thickness do you need for a climber to grip onto? We don't really know the answer to that yet, and it would depend on the engineering for the gripping mechanism. The width is certainly going to be important, and the width is likely going to be changing as we go up in altitude. And so the friction is certainly a concern, and I don't think we have a minimum width in mind yet, although that's certainly something we have to come up with.
All right, I think we'll be moving on now. I see Adrian has mentioned that the gaseous phase for the repair is one kind of possibility, but I think we'll move on to our next section.
All right, great. So that was statics. We, I think, demonstrated that the space elevator would stay up if it were static, in fact, not moving. But in a real world, things are going to be moving, and so I have a picture here of 3 different modes of the space elevator, if you believe it. On the left-hand side is a picture of a vibrating string. This is the mode that we hope it'll be in most often. So it will be stretched tight by gravity and centrifugal force, and something is always going to happen to make it vibrate. And so there will be hopefully controlled vibrations that are always happening, and we would probably take active measures to make sure that the vibrations do not become too large. So left-hand side is the preferred mode, vibrating string. If you look on a smaller scale, that is the scale of the climber, so we're talking maybe from 5 to 10 meters, then the space elevator cable looks quite different. It's going to be a very strong material, and it's going to be under great tension. It will be very similar in stiffness to a metal beam. And so there will be some very high frequencies. It would almost ring if you hit it with a hammer. And that has some consequences for the climbers, because if indeed it is very stiff, then the climber wheels might have trouble negotiating that, and that would affect how we design the climber. So those are 2 expected modes of oscillation and movement of the tether. On the right-hand side is a strand of spaghetti. Okay, this is something we don't want to have happen, but it's possible. So suppose for some reason the tether could lose tension. We can, in some degree, predict what will happen to the tether. So this would be in the unfortunate circumstance of a break. And we can predict the path of the tether and more or less what it's going to look like as it flows freely, so to speak. So that's another mode that we have to consider, and I'll discuss that at the very end. One of the essential items of space elevator dynamics is called the gravity gradient stabilization. So we mentioned that the space elevator will stay up by a simple balance of forces, but what if we kick it from side to side? So we have some tidal forces or some perturbations from the non-sphericity of the Earth or anything like that, collision, could cause it to be knocked off. What's going to happen then? Well, if you have any long object in orbit, it naturally wants to orient itself up and down, that is, on a line pointing through the center of the Earth. And if it is bumped, then it's momentarily off vertical, but it always wants to come back to vertical. So why is this? So I've drawn a hypothetical object in orbit, and to each end of this object, I have the forces, gravitational forces listed. Now, as the lower end of this object is deeper in the gravity well of the Earth, the force on that end is very large. The upper end of that object is further away from the center of the Earth, so the gravitational force is less. So it's the differential force, and the component toward the vertical is always going to pull it toward the vertical. So the lower line has a bigger component toward the vertical than the upper component. And so the difference of those two always brings the thing back into vertical. And that's the main thing that keeps the space elevator on the vertical line. And at this point, I think we have another poll.
There is no
So I didn't give you entirely.
Go ahead, Dennis.
Oh, okay. I didn't tell entirely the full story, and so I'm going to let you decide what I didn't tell you.
And so everyone's voting. There's no submit button, as you probably have figured out. And we'll be broadcasting those results in just a couple of minutes, or actually seconds. I'm going to give you a few seconds more to vote, and then I'll broadcast those results. All right. So here are our results.
Okay, very interesting. So, gee, it's getting pretty close now. That's what a teacher doesn't like to see. Oh well. So the length of the object looks like the plurality right now. Centrifugal force and mass of the object are tied. Okay, all of these things are important, but the thing that is most important that I left out is centrifugal force. So I was talking about an object which is dominated by gravity. And so, as we saw on one of the earlier slides, if you are below geosynchronous orbit, then gravity is the dominant force, and this gravity gradient stabilization is essentially the only thing going on. But as you go further and further out, when the centrifugal force becomes more important, then that starts to dominate, especially as you get beyond geosynchronous orbit. And that's the reason I didn't mention it at the first place. It complicates things. The point is that when you add all of this in, centrifugal force and the gravity, then the gravity gradient stabilization still remains dominant, even if you go further out. It's just has less of a net effect. And so, very interesting poll. Oh, I see people are still voting. Great. So centrifugal force has gone up to 42%, 47%. Great. Okay. So let's go on. And another way to get a good idea of the dynamics of a space elevator is one of these things. You've probably seen these in a museum or a mall. And I think most of the time they're called wishing wells or something like that. But since this is a science talk, we're going to call it a gravity well analog device. Now, you put your quarter in, it spirals around, and looked at from above, it really does a good job of tracing out a Keplerian orbit. And so you can imagine using these things to do all sorts of orbital studies. Now, for the space elevator, let's take one step further and take this funnel and perforate it with holes and then force some air through it so that we have a combination of a wishing well and an air table. And then you can imagine floating a string which goes from the bottom of the well out to the edge. And so that is simulating then a space elevator attached to the Earth and going out to 100,000 kilometers or whatever our scale length is going to be. So it's going to be floating there. And even just looking at this device, you can see how deep the Earth's gravity well is. And so the Earth is down at the bottom there, and you can't even see it on this picture. And so it's a challenge to get out of that gravity well. Now, the utility of this device is that you can imagine that you are taking three-dimensional space and then getting rid of one of them and using this gravity well to represent gravity. And so that when you look above and down onto this, you can get an idea of what the space elevator will look like as it rotates along with the Earth. So let's suppose now that we have this string which is floating from the depth of the gravity well out to the edge, and we set it to rotate around this wishing well. Right away you can see, if you're looking at it from the top, that there's no place for it to move when it's down, the end that is down in the gravity well. And so looked at from above, if you're taking a movie of it, you can see very little motion in the central area. Whereas if you go to the outer areas, you see there's a lot of region for moving around, and therefore a lot of region for vibration and oscillations and things like that. So I like this because it gives you an intuitive idea of how these things would move and what dominates the dynamics of a space elevator. Oscillations are going to be an important part. So when I talked about gravity gradient stabilization, and we said that we were going to take this object and knock it off center, it always tries to come back, but as it comes back, it always overshoots. And then it will try to come back the other way. Eventually, it stabilizes. But these oscillations are going to be important, and whether or not we can damp the oscillations are going to be important too. And so an object is going to try to get back to vertical. It's going to head back the other way, cause oscillations. One of the common modes and the largest mode that we have to deal with the space elevator is something called libration. So regardless of your physical arrangement of the tether, it could have wiggles in it, it could have kinks in it, it will always have this main mode in which it rocks back and forth as if it were a solid rod. On top of that, there will be some oscillations, but the main oscillation will be this solid rod oscillation. And one way to look at that is to take your Physics 101 pendulum, turn it upside down, and put it in a gravitational field, and that's what you've got. And so the length will depend, will give you the frequency. Because it's a space elevator and because we're in a gravitational field, it's more complicated than that. But you can do all the usual things like work out its resonant frequencies. And in this case, for a 100,000 kilometer long space elevator, the lowest mode for oscillation is 5.8 days. So it's going to take nearly a week to go from one side to the other and back. Now, these normal modes of oscillation are going to be important because we want to try to avoid exciting them. And if, for example, we had built a space elevator which had a frequency of 7 days, then we might be in a bit of trouble because we have the moon coming around every 28 days. And so we're in a 1 to 4 resonance situation, and that could easily excite oscillations in the space elevator, and we don't want to do that. So that's why it's important to figure out what the normal modes should be, and adjust the mass and the length accordingly. And we can go on to the higher modes. So I talked about the libration mode, in which we could do the calculation as if the space elevator were rigid. You can now start breaking it up into smaller and shorter rods. So for example, you could break it into 2 rods, which pivot at geosynchronous orbit, for example. And then you would have a double pendulum. So now we have 2 connected rods, which can rotate independently of one another, but they still swing back and forth. And the reason I bring up this example is not only is it a nice graduate student level calculation to do the double pendulum, but this is the system in which you can have chaotic motion. So there is, in fact, I saw some while ago a YouTube of a double pendulum in which they demonstrated this chaotic or non-predictable motion. That usually only happens when the oscillations are big, and so thankfully we don't have to worry about that, but it is a concern that we know what the size of these oscillations are, and we calculate all of these higher modes. And once again, these modes can be driven by other things like the gravity of the moon or the sun, and we want to be very careful about that. Now we get into some more complications. The picture here at the right is from a space elevator climber competition in Japan. And sorry about the quality of the picture. The screen capture didn't work very well, but what you see there is one of the climbers, and there's a tether that it's climbing. And it demonstrates a couple of the things that I wanted to show. First of all, you see a kink in it. So obviously something like that is going to happen. And then you see that the cable, the tether itself is twisted. So these things are going to happen in a real space elevator. So we're going to have transverse waves. So the ones I talked about on the previous slides, it's going to swing back and forth a little bit, vibrate in and out of the orbital plane, just like a vibrating string. And for one reason or another, the climber is going to induce torsion waves. And so there's going to be a twist. And as we hang the weight on the tether is going to stretch. And for the materials that we're looking at, the stretch is going to be probably about 3%. So out of 100,000 kilometers, we're going to have 3,000 kilometers of stretch. So that's a lot. And once you put this extra tension on the tether, then you have compression waves. So all of this is happening at the same time: transverse waves, torsion waves, compression waves, and this is where the math gets really ugly. So we do our best to separate these things out, but in some cases they're rather tightly coupled, and it's really computer intensive to get some of these calculations going. Now, I believe it's time for some more Q&A.
Yeah, so if anyone has any questions, I think we've answered them, or Pete has answered them as well. So if anyone has any additional questions, please type them in chat. I see some people are typing. So are there any researchers of traveling wave has come in? I think there's more to that question.
Mm-hmm. And the early answer is yes.
Can today's computing power handle the calculations?
Yes, very good question, and that's something that we at ISEC are working on. So we want to build a simulator of the space elevator, and there are calculations now that treat it as a series of rigid links, 1,000 rigid rods, which are connected by springs. And that calculation is pretty reasonable with respect to CPU time. But if you really want to put all of the things in that I was talking about, like the torsion and the vibrations in both in the orbital plane and out of the orbital plane, it starts to become rather intensive. And so one of the things we want to look at is how do we employ things like graphical processing units to do the really intense calculations. So yes, the short answer is the CPUs exist, and now we just have to write the code.
Okay, and then in regards to climber competitions, Winston is interested in learning more about the prevalent methods of energy logistics for use of the climber.
Very good. I would say for the quick answer is to go to the ISEC website and look at our 2013 study. So if you go to the main page and look at resources and under studies, we do an annual study. And in 2013, they looked at energy consumption and energy design for climbers.
Okay, and then a question, can the waves be canceled by deliberately vibrating the
Yes, yes, indeed. So not only can you do it by vibrating the cable, but another way to do it is by strategically launching climbers. I'm going to talk about that in a little bit, so I won't say too much more. But yes, yes, inducing counter waves into the tether would be one way to help reduce the oscillations.
Okay, and here's a question about stability or instability. How much would you add to the system if you had multiple space elevators in parallel or perhaps at different connected length heights?
Yeah, okay. So our current design for the galactic harbor has, in fact, multiple parallel space elevators. That is something that at least I can understand physically. However, when you start coupling them together with perhaps crosslinks, that's something that I myself have not studied. There are codes out there for looking at coupling tethers together in orbit in networks. Um, but I'm not really familiar with those. I assume it can be done, but I'm not familiar with the dynamics of that.
Okay, and then given the design descriptions of the tether in this presentation, what is the range of allowable mass of the climber and payload?
Okay. The tether that we are envisioning now, we call it the initial operating capability of the space elevator, assumes that we'll have about 20 metric tons for the climber. And there are other studies in which they are looking at much heavier climbers, and so they could go up to 100 metric tons or more. But as you increase the mass of the climber, the mass of the tether goes up too. So it's proportional. And it then eventually it comes down to just how much material do you have to make a tether with. But I don't know of an upper limit. As long as you can balance the force, then build a bigger climber.
All right, I think we'll move on to our next section about climbers.
Right. How does a climber climb? So we'll first look at friction. We have to grip the tether in some way, and this goes back to one of the earlier questions: is how much area do you need? Two ways to do it. You can either deform the wheel, so you have a pinched wheel situation in which the tether itself is not deformed, but the wheel is. And so the deformation energy goes into the wheel, and that accumulates there as heat and fatigue. The other thing you can do is deform the tether and not the wheel. And so now the energy accumulates in the tether. So obviously we would like to reduce energy that accumulates, which we have to dissipate because heat dissipation in space is very difficult. But one of these is probably the way to go for a mechanical climber. And we are probably going to have another annual study coming up very soon in which we will look at this very effect. Another way to look at it would be electromagnetically. So rather than physically gripping the climber with the wheels, we could do something like a linear induction motor. So over on the right at the top is a cross section of such a thing, and we have in the magenta squares some coils, and currents are running there to generate a magnetic field. And the magnetic field is generated, propagates out, and then you see that boundary at the yellow region there, where the field starts to penetrate what in this case would be the tether. And so it takes a little time for the field to penetrate the material of the tether. It sets up eddy currents, and that sets up a counteracting magnetic field. And so that counteracting magnetic field then repels the field generated by the original coils, and then you have a forward motion from that. So that's the concept of a linear induction motor. This at least is probably the option that I like, because no wear and tear on the tether. There are there's a diagram in the center right of what this might look like. And very interesting at the bottom is a working prototype of one of these things. And this, I believe, was generated for JAXA, the Japanese Space Agency, to fly on one of the tether tests that they're doing. And the interesting thing there is that you can see the coils and the armature that holds them. And it's straddling a very thin tape, and that is copper. And if you look carefully, you can actually see through the copper. So the copper is very thin enough to see through, but that is enough to support the eddy currents and the counteracting magnetic fields that drive this thing. And so this gives you an idea of just how thin, perhaps, we could make the space elevator tether. And there's another very interesting option developed by John Knappman, also one of our members. This is the electrostatic wheel. And so if you look at one of these wheels, you see what it is, in fact, is a drum of conducting plates. And so each of these plates is, I think, about a centimeter long or something like that, and then extends into and out of the page here by several centimeters, so that you have plates. And these plates are on the outside of this drum. The tether is a conducting surface, and in this case it is deformed. But notice that there is a gap between the tether and one of the plates of the wheel. Now, if you put a voltage, a rather large voltage, 10 megavolts, across this gap, then the plate and the tether draw themselves together, and there is an upward component, and the wheel will rotate and it will go up. So the force between the plates is kind of like a capacitor. It has an upward force because they're not parallel, and that draws the tether, the climber up. And it looks like 5 of such wheels could lift a 20-ton tether. So this is a rather ingenious solution to the problem. It would deform the tether, but there would be no frictional contact. So that's a nice aspect. Now, back to dynamics and the effects of climbers on the tether. We go back to the fact that we are in a rotating reference frame. So we're looking at all of this from some place on the ground and observing what happens, but everything is rotating. And so we have
Dennis?
not only centrifugal force, but we have Coriolis effects. So the same force that is causing our weather patterns will also cause the tether climber to deflect. So a moving climber is going to pull on the tether, and as I said, it creates all of these waves. But the way in which it does it with the Coriolis effect is as follows. So if we look at the right-hand plot, you can see a picture of a tether, or a climber, climbing the tether at about 200 kilometers per hour, and it's near geosynchronous orbit. In that configuration, there's going to be this little kink. I think you can probably see that black line is not straight. It deviates from the red dotted line. But that is because, in fact, the tether or the climber wants to go into an orbit, but the tether is holding it back. And so that's causing the kink. And this residual force is going to cause the tether to be deflected from vertical. And if we're not careful, this induces that libration mode that I talked of, that large pendulum-like motion of the tether. And we can actually induce an oscillation which can grow to be rather large, even though here, in a normal operating circumstance, that angle is very, very small. But we do have to keep that in mind. Now, if we were to stop the tether suddenly, that produces another force which increases the oscillation. So we don't want to do that. We can, however, counteract that by launching tethers at various intervals, and that minimizes the amount of deflection. So that answers one of the questions that was asked earlier about counteracting the effect of the tether. But there's no way to get rid of it entirely. It's a force that exists, and we just have to plan for it. Okay, now I believe we're due for
Yes, we have some
more
questions.
Yes.
But before we do that, I wanted to just circle back to this poll about climber traction.
Yes.
So I'm going to have everybody vote and just give us your ideas of what you think would work best. If you think something else, if you have something else, please type it in chat. As we are a member organization, we love getting new ideas and new eyes on this space elevator solution, and we'd love to have your input. And as Pete says there, we'd love to have you join us, and we are approaching our 2021 year-long study. So email info@isec.org to volunteer. I'm seeing results coming in. I'm going to give everyone a few more seconds. Okay, and I'm going to go ahead and end the poll in about 5 seconds, so get your votes in if you haven't voted. And this time I'm going to close the poll and show everyone the results.
Okay, so linear induction motor, the clear winner. I think so too, but could be some other options out there still. So that's why we like to see if anybody is thinking of other things. Okay, great.
Okay, and now we'll get to our questions. So can heat produced be used to generate electricity to power the climber?
Heat. Interesting idea. I don't really know. We always think about how to get rid of heat, but we never think about how to use it. So I'll just say I haven't thought about that one. That's a good one.
So we'll keep that in mind. So that's an interesting thought there. How well does that work on the graphene tether? And that's from Kevin, and I'm not sure what that is in reference to. So maybe you could expand in the chat. And then we also have, has anyone done calculations on the currents required and its effect on the graphene?
Currents required for the electrostatic wheel, or?
Well, Larry,
some clarification.
Yeah, Larry, could you clarify that for us? And Kevin has clarified his about how well does the linear induction motor work on the graphene tether.
On the graphene tether. That will depend on the material properties of graphene. I understand from Adrian that the conductivity is very, very good. And so it might work very, very well.
Well, that's great to know. And then Larry clarified his calculations on the currents required and its effect on graphene is in regards to the induction motor.
Okay. Yeah.
So do you know of anyone who's done calculations?
I don't believe anyone has yet, because we still don't know just what the conductivity is. Also, because it is essentially a single molecule, we have a really interesting situation where we've got some fairly strong electromagnetic forces that I don't think anybody has actually looked at in terms of propulsion and things like that. So, we usually deal with fairly weak things because we're dealing weak forces, that is, because we're dealing at distances of, we're talking millimeters for linear induction motor and things like that. But conceivably, we could get a lot closer to single crystal graphene and start using the atomic orbitals. I don't know. That might be really out there, but um, I understand the the atomic orbital orientation in single crystal graphene is unique because of the pi bonds of the electrons, and so that could present a very interesting scenario for propulsion. Also, that I understand that if single crystal graphene is put together in a certain way, it may even be a superconductor.
Oh, that's really interesting. We are actually at the end of our stated time, but we do have a good deal more of our presentation, so we do apologize if you need to drop off. But we will continue the presentation for as long as you would like, or at least a reasonable amount. There is a dish, so we are recording, so if you need to drop off for other commitments, we do apologize that you won't be here for that, but the recording will be on YouTube as well as the ISEC website. So thank you, and I hope you can stay on with us. We have another question. What is the expected temperature range on the space elevator Tether?
Oh, probably going to be pretty large. I don't know exactly, but I would expect it to be pretty much the same temperature range that is observed in most satellites, International Space Station, and so on. So getting pretty cold to pretty hot.
Okay, well, we'll move on to the next section on space elevator environment. This is one of my favorite graphics. I love this graphic.
Yeah, this is something that I took from NASA and then put a few additions of my own. So what I've done here is to put the space elevator in green, and that is to scale. So you can see what size it is with respect to the Earth and some of the interesting aspects of where it goes. So one of the first things you noticed is that it sticks right outside the bow shock. So this is where the solar wind is coming in and impacting with the magnetosphere. And that basically creates a kind of a current sheet. So that's the first electrical phenomenon that we would have to deal with. And then as you go further in, you're getting into the magnetosphere, and further in still, you see the magenta is the Van Allen belts. Those are sort of medium energy protons and electrons. And then the brown area is the plasma sphere. Those are lower energy particles, mostly electrons. And all of these things make for a rather complicated arrangement for the space elevator to live in. Very dynamic, too. And so if you ever saw an animation of the magnetosphere as a function of time, it would it reminds me of a kind of a fish swimming upstream. So if you think of the solar wind as the stream, and the magnetosphere is swimming upstream. It's the tail out here where you have the magnetopause and the magnetotail. That's flapping about a little bit, and the head of the fish is angling off. And so it's really interesting to see if you ever get a chance to see an animation of the magnetosphere. So let's go on and talk about the first aspect, which is electrodynamics. So here we have a lot of forces going on. Lorentz force. So this is the sum of the electric and magnetic forces on charges. And a lot of this for the space elevator is going to depend on just how conductive it is. If you're using carbon nanotubes, some people say that it will be not conductive. And in fact, even an insulator. And so this would not really make much of a difference. If you're using single crystal graphene, we think it could be very, very conductive. And so the forces will be significant. And a lot of the calculations that have been done so far with electromagnetics on the space elevator have shown that the forces can be sizable. So let's look a little bit about the physics of this. The magnetic force, or the B force, is always perpendicular to the velocity in the magnetic field. So in the picture at the top right, you have the magnetosphere of the Earth, and I have drawn a location marked by the X. And in the normal convention, that means that this is something which is moving into the page. So you're seeing the tail of the arrow, in a sense. The red arrow, straight red arrow, represents the strength of the magnetic field at that point and direction. And the blue represents the force which this particle or satellite or what have you would experience. And so if this particle is moving with respect to the magnetic field, you're going to get an outward force. There's also electric force. And so if you have charges, you're going to have an electric potential and therefore an electric field. So down at the bottom, you see something which is the electric field. We don't see this normally when we look at pictures of the magnetosphere and the Earth, but because of the solar wind interacting with the magnetosphere, an electric potential is set up, and it is rather sizable. And so what I've done here is taken the picture of the electric potential, and you can see the Earth at the center, and I've drawn the electric field. So the electric field lines are always perpendicular to the potential lines. And keep in mind now that a space elevator would be attached to the Earth and would go radially outward. You can see that, yes, if this elevator is conductive, then currents will flow. So as I mentioned, the environment is dynamic. The dipole field is not symmetric. A lot of the pictures show it that way, but it's not. It's not even completely dipole, actually. The day and night side are quite different, as you saw from the diagram. And I also mentioned that you see lots of time-dependent wobbles. We have compression and expansion of the magnetosphere because of solar activity. And the electromagnetic charging is also something that we have to consider for a space elevator. We can easily achieve voltages in the kilovolt range. And this is something that satellite designers already know about and know how to deal with. So many instabilities. As I mentioned, we can actually have sizable forces. In this case, if we have one of the big X-class solar storms, then the fact that the magnetosphere is changing and that electrostatic potential that I mentioned is also changing, this could cause the apex anchor to move as much as 6,000 kilometers. So this is a huge amount. I mean, we're talking the radius of the Earth here, and that's the endpoint. So thankfully, these X-class storms don't happen a lot, but it's something that we have to know about. Power generation is an interesting possibility. I did some calculations myself, and in fact, you can get a little power generated on a conductive tether if it's a really good conductor, but it's not a lot. It turns out probably would only be warm to your hand if you touched it. So right now, it doesn't look like a great way to generate power. All right. Now, the other thing, besides electromagnetism, we have to worry about is radiation. So the space elevator will extend through 3 different radiation regimes. We'll have the solar wind, so these are protons and helium nuclei from the sun. Van Allen belts, protons and electrons that build up because of the solar wind. And then the galactic cosmic rays. So these are very high energy atomic nuclei ranging all the way up to iron, which are probably produced in supernova explosions. So all of these are contributing to the radioactive stew, so to speak, that we have to deal with. And we need to deal with this. And the typical ways to do it are the 3 rules of radiation. You can do it by shielding, time, and distance. And now we have a poll coming up.
All right, so we have which of these combinations do you think the space elevator climber will need? And those are the shielding, time, and distance. So 1 is shielding, time is 2, 3 is distance. And we need to understand what will be needed in order to take human passengers. So if you think we need both all shielding, time, and distance, that's the first answer. If you think we only need shielding and time, that's the second answer. And if you think we only need the distance, that's the third answer. And of course, tongue-in-cheek, we have our fourth answer. Wait until you're 65 years old, then it doesn't matter. Of course, maybe we want to change that to 90, I don't know, but little tongue-in-cheek there.
I put that in. It's not entirely ridiculous because there's a study showing that as you get older, your tolerance for radiation increases. And this, I put 65 because that is the year when it starts to really make a difference.
Oh,
So I advocate for senior citizen astronauts.
oh, I love your idea, Dennis. I didn't know that. That is really interesting. So our tolerance for radiation. So we could instead of that's really yeah, senior citizen astronauts. I'm really on board with that one. And so I am going to go ahead and end our poll, and I'm going to broadcast our results. So 40% of you think we need all three, shielding, time, and distance, and 36% think we need the shielding and the time, 8% just the distance, and of course, with Dennis' comments, 16% of you say, hey, let's wait until we're senior citizens.
Yeah. Okay, well, what I will say is that yes, we would like 1, 2, and 3, but we cannot get 1, 2, and 3. So, first of all, space elevator is going right through the Van Allen belts. So we can't use distance. Distance is not our friend. We also cannot use time. We can't get through the radiation belts very quickly. So a typical velocity for a climber is going to be 200 kilometers per hour. The Apollo astronauts zipped through the radiation belt so fast that they got a minimum dose. So they were actually able to minimize their time. We cannot do that. So we're going to be stuck right in the middle of the belt for about a week. So that comes out to about, well, very close to a lethal dose. So this is not good. We have only then to rely on the shielding. So let's go to the next, go to the slides. So radiation shielding is the only thing we have left to deal with if we want to send humans in the space elevator. And let's talk a little bit about what happens. So we have the low energy particles that I mentioned, the protons and the electrons, and most of this can be done with lead shielding. Enough lead shielding, you can block it all out, but it's heavy. So that's not so good. There are the medium energy particles. So these are some of the solar wind protons and particles like that. This gets a little bit more tricky because if you just put some lead, you can actually create more trouble than you started because now you have neutrons. Particles come in with the lead, they can liberate neutrons. Neutrons stay around for tens of minutes, and so that's another radiation source that you have created. And so you have to be careful, and something better than that will be needed. One thing that people would like to use in a situation like that is borated hydrocarbon. Not only does hydrogen absorb neutrons very well, but the boron has a very high neutron cross-section, so that's another excellent shielding material. And a side note, you probably recall on one of the very early slides in this talk that boron nitride was a possible material for the tether. So wouldn't that be great if we had a tether made of boron nitride and the boron could absorb the neutrons that might be created. High energy particles, so these are the iron nuclei and very high energy particles from supernova explosions and things like that. Nothing you can do about them. The magnetic fields, even today available at high energy particle detectors, aren't going to be enough, and they're heavy to boot. So we just have to forget about those and count on the fact that they are relatively quite rare. Okay, more on shielding comes next. Here's the results of another NASA advanced concept study in which they were looking at space settlements. And so they say, well, we have all of this radiation. What are we going to do for people living on lunar surface or out in space? And so they came up with a series of solenoidal magnets, and you can see those by this ring of blue circles. Well, first let's start from the center and work out. This larger circle, which is a blue circle in the center, represents the region of the habitat, whatever that may be. And then surrounding that is a set of smaller blue circles, and each of these smaller blue circles represents a solenoid, and that creates a magnetic field which goes directly into the page or out of the page. So you're looking down into the field. And so this feature of magnetic field being constant or more or less intense rather inside the solenoid deflects any outcoming particles. So you have these cosmic rays. I think these are about 1 GeV particles coming in, and they encounter the magnetic field and they are bent at 90 degrees, and so they are turned back out from whence they came. Now, it's not 100% efficient. Some particles, depending on their angle, as you can see by the black solid line and dotted line, are deflected, but they happen to be deflected right through the habitat. Fortunately, a lot of them are deflected away so that you really do significantly reduce the radiation inside the habitat area. So we could consider this for shielding for the space elevator climber, but always it adds weight. And so we think that maybe for the first ones, it's going to be wise to make the first space elevator a freight elevator. And we can worry about people later, or perhaps the best thing to do for that is to leave the passenger traffic to the rockets and leave the freights to the space elevator. And finally, we have the effects of the atmosphere. So the last environmental area that we consider, lots of weather effects below 40 kilometers. So high winds, this produces a transverse loading on the tether. And you can probably think about what happens when you look at a flagpole with a lanyard attached at both ends in a wind. So that starts vibrating and it's slamming against the flagpole, and it just happens over and over and over again, and so the wind causes a driven oscillation. And so high winds would do the same on the tether. Lightning, also a problem. One thing we can do is definitely reduce the frequency of lighting by where we put the space elevator. On the equator, frequency of lightning is quite a bit smaller. Rain, corrosion, electrical problems due to that. So all of these things have to be dealt with. Chemical effects are a problem. So in low Earth orbit, for example, we have monatomic oxygen, which is corrosive, as is ozone, which is between 17 and 23 kilometers in altitude. Conceivably, both of these things could attack the tether. I understand that single crystal graphene is rather resistant to these attacks, so that's another nice feature of that material. But all of these things are concerns. And finally, space debris. So I'm not going to spend much time on this because we have 2 annual studies that have dealt extensively with this. The 2010 study just did the first look at this, and the 2020 study just out is also a review of this, given the increased number of objects up there. And the conclusion from both of these, as updated recently, is that the threat due to space debris is in fact manageable with both active and passive measures. So it's a problem, but we can do something about it, and we can do enough about it that keeps the space elevator safe. However, let's talk about worst case scenarios. What happens when a severance does occur? So at low Earth orbit, this is where we have most of the junk, and so the possibility of a severance is higher. The tether is usually going to drift slowly upward. That is, the remainder, the severed part, will drift slowly upward. This gives us some time to recover it. So you can conceive of paying out more tether from above, so that you put more mass down into the gravity well, and that would stabilize it. That's one thing you could do. Probably the worst case situation is where there is a sever right below the apex anchor. So at the very far end of the space elevator, then all of the tether is at risk, and it may start to come down. We could think of some measures to counteract that, but I think that is one of the more difficult problems to solve. So that's an interesting one. The saving grace here is that a severance event at that altitude is quite rare, since there is almost no junk up there. And that concludes my talk. And I do have a final poll about what you would like to see in the future.
And this is a fill in the blank, so you can type anything you'd like in that what topics you would like to see covered in future webinars. We're building out our next series of webinars in the coming days, and well, actually in the coming months, and we'd just like to get your input as to what you might be interested in. And you cannot see anybody else's responses, just your own. I'm going to leave this up here for a few minutes. We're past our time, and I need to close out the session. So please go ahead and give us your examples of what you'd like us to see in the upcoming webinar. I'm just going to give a few more seconds, and of course if you do have any other kinds of suggestions and you didn't quite get it into the poll, you can email info@isec.org. Give us your specific recommendations, and you can also email me. My name is Karen Gleason, and I've been your producer today at kgleason@isec.org, and I can collate and curate those answers and get them to the team. And with that, I'm going to go ahead and end our poll and move back to our introduction here. And I just want to thank Dennis Wright for putting together that great presentation for us. So thank you, Dennis. And thank you.
You're welcome.
I have another thank you there. So we do want you to stay in touch with us. When you go to isec.org, at the bottom of the page, you can sign up for our newsletter, which you'll receive monthly. And we have a lot of great resources available on our website as well, all complimentary to you. However, we would love you to join our family here at ISEC, to become a member. As you see, our membership is extremely reasonable, and you will have access to a number of different things in our membership. We actually have a members-only webinar, or I should say more or less a roundtable coming up, where we just sit around and discuss things. And it's going to be in a different format, and everyone will be able to talk. I know in a webinar situation it can be difficult because you can only type in chat. But we're going to open it up and have our members present some topics, as well as we're going to have some open discussion. So if you'd like to find out about our next open webinar or our members-only webinar, we'll get those up on our website shortly, and you go to isec.org/events. And lastly, we do want to thank our sponsors for this event, the Adobe Connect, which is the platform I'm using, the Learning Guild that's allowing us to use their platform, and I am Karen Gleason. I've been your webinar producer for today. So if you'd like to find out anything more about us, you can click those logos there and find out more. So with that, I'm going to say thank you to everyone for spending their time with us today, and we look forward to seeing you next time.